All right, so now we're going to start talking about some of the reactions that carbohydrates undergo. The good news is that we've already kind of gone over these when we did our organic chemistry portion of the course, right? So we're going to be focusing on those ketone or aldehyde groups in a sugar, and those can be oxidized or reduced. And yeah, so, again, it's all about the reactions of sugar, specifically oxidation and reduction reaction. It turns out that when you reduce sugar, you get what's called sugar alcohol. And these are still perceived by our taste buds as being sweet, but they can't be digested by our bodies into energy. So in that way, these reduced sugars or sugar alcohols are used in diet drinks and sugar-free products and other sort of as a flavor ingredient to give you that sensation of sweetness without the calories, without your body's ability to break it down. We're actually going to talk about sugar acids first, okay? So what happens when we take, for example, the open chain form of glucose, which has this aldehyde group, and we oxidize it? What happens when we oxidize aldehydes? What do we get? We get carboxylic acids. So notice nothing else has changed. The only thing that's changed is the aldehyde going to a carboxylic acid. All those other alcohol groups stay the same. Okay, this is using a particular oxidizing agent known as Benedict's reagent. You might remember that we used something similar in the lab when we did our experiment on aldehydes and ketones. We used Holland's agent. Benedict's is the same sort of idea. It gives you this color change. Actually the lab manual was written to use it and we didn't use it. But anyways, all it's doing is oxidizing an aldehyde to a carboxylic acid. And so that's exactly what we see for ketones, or specifically for aldoses, right? Ketones that have those aldehyde functional groups. And if you remember back to what we were talking about before, when you go inside of a human body and you grab a sugar, it's in that closed chain form. But remember that closed chain form is in equilibrium with the open chain form, right? It's going from the beta isomer to the open chain to the alpha isomer and back again. So if we were to mix a sugar in with this, this oxidizing agent, yeah, it wouldn't work on that closed chain form, but that chain is always opening and then reclosing again. So that's how you can lead to the oxidation of sugars. Let's look at the name real quick. We go from being glucose with that ose ending to gluconic acid. Right, so for when we were talking about organic chemistry, it was oic acid. However, in biochemistry, it's going to be onic acid when we're talking about sugars. So you take whatever that sugar is, mannose would go to mannonic acid. Fructose would, fructose actually wouldn't work because it's a ketose. Galactose would go to galactonic acid, et cetera, et cetera. Okay, so that's the oxidation of sugars. Yes. We can do that using, for our aldoses, using, again, that Benedict's reagent, which is copper with a 2+ charge, and then it gets reduced to copper with a 1+ charge. And again, we're going to replace the name of the sugar, the ose, with onic acid. Sugars that have free aldehydes are going to be called reducing sugars. Okay, that is sugars that can open when they're in their closed chain, they open back up and they have an aldehyde. That's a reducing sugar. Fructose is a ketohexose, right? So it contains that ketone group. Ketones can't be oxidized. However, what happens when you put this in a solution with Benedict's reagent is it actually undergoes a rearrangement between the ketone group on carbon 2 and the hydroxyl group on carbon 1, and is thus converted into glucose. So even though fructose is a ketohexose, it can still be oxidized because actually first it rearranges itself and becomes glucose and then can be oxidized. So for example, so this is fructose here. Again, in the presence of Benedict solution, we wouldn't expect a ketone to be able to be oxidized, right? However, because its position, really because there's this hydroxyl group here, it can rearrange itself and form an aldose, which in this case would be just glucose, and glucose can be oxidized. So even ketoses are oxidizable as well because of this rearrangement that's available. Okay, so aldoses and ketoses are reducing sugars. And any monosaccharide is thus going to be a reducing sugar because they can always form that open chain form, which is either going to be a ketone or a ketose or an aldose. Okay. We're going to see some polysaccharides cannot open back up. And so those would not be reducing sugars. So there's sort of a punchline that we're getting here by classifying things as reducing sugars. Again, if it's in its open chain form and it's either an aldose or a ketose, which is all monosaccharides, they're reducing sugars. We'll see some examples of non-reducing sugars as well. Okay, so then we can do the opposite of an oxidation, which is a reduction, and aldehydes and ketones both will be reduced to alcohols. So taking that aldehyde or ketone group, we can reduce it and convert that aldehyde to an alcohol. Okay, if we look at the name here, what happens, we're going from glucose to glucitol. All right, so replacing that ose ending with itol. There's also sorbitol is kind of a common name that's used specifically for glucose. So I don't want to spend too much time on that. It's because glucose is so common and the reduced form of glucose is so common. It's got its own special name. I want to focus more on how we go from the existing sugars that we know about. So for example, glucose, glucose, when that gets reduced, we get glucitol. Okay, so being able to replace those endings and forming that alcohol is going to be important. Okay, so again, replacing the ose with itol, that's how we go get the sugar name. All right, and again, what happens when we reduce glucose? Again, focus on this group here. Nothing else is going to change, but that aldehyde group will be reduced to an alcohol. Whoops. And again, what we're going to learn is replacing that ose ending with itol. I don't want to focus on the common names. All right, so here's the change in functional group that we see from aldehyde to alcohol, and here's the change in nomenclature that we see going from ose to itol. And again, these are used as sweeteners. Okay, so the whole shtick is that your tongue still detects it as a sugar, but your body can't metabolize it like a sugar. So now we have this other sugar here, mannose. Let's see if we can't figure out what the structure will look like for the reduced form of this sugar, and let's name it as well. So what I'm going to do is first make sure I have all of my correct carbons. Put the achiral ones in first. 3, 4. Nothing's happening to these chiral carbons and the hydroxyl groups on there. So I'm going to draw them all the exact same as what they were before. All right, the big difference is going to be on this first carbon here, carbon 1. I guess just to get in the habit of naming them or numbering them as well, right? If I were to number my carbons, that would be what I would get. All right, that's another skill we want to be able to have. And instead of being an aldehyde, now we have a alcohol. So this would be just CH2OH. That would be the reduced form of mannose, which would be D-mannitol. All right, I'm going to replace that ose ending with etol. Okay, so then this is the idea of this sugar. Again, all monosaccharides are this idea of a reducing sugar. All monosaccharides are reducing sugars because they can open up to ketones or to ketoses or aldoses. If we're looking at the closed chain form of a sugar, okay, what we're going to be looking for is a free OH group on the anomeric carbon. Okay, so any time we're given the closed chain form of a sugar, whether it's a monosaccharide, a disaccharide, a polysaccharide, if we're being asked, is this a reducing sugar, what we're going to do is look at the anomeric carbon and see if it has a free OH group. In this case, there is a free OH group, so this is a reducing sugar. In addition to being able to be reduced by reducing agents such as hydrogen gas over palladium or nickel, reducing sugars can react with alcohols to form what are called glycosidic bonds. And this is going to be something that's really important when we start talking about disaccharides, is this formation of a glycosidic bond. So, right, we have this alcohol forming with that OH group. This is now going to be a glycosidic bond that's formed here. If we were in organic chemistry, we would call that an ether, right? And a carbon, oxygen, carbon. Now that we're in biochemistry and we're looking at carbohydrates, this is what's called a glycosidic bond, okay? And so, yeah, this is just the reaction of a reducing sugar, specifically that free OH group on that anomeric carbon, with any sort of an alcohol, and they form this glycosidic bond, which is now a carbon, oxygen, carbon set of bonds.